Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we will continue the discussion of dispersion, and we do so by going back to this channel and then the problem of having to find out what would be the output electric field E of LT when I know what is the input electric field E of 0t, and because I know the input, I also know the spectrum, okay, which I have written as E0 omega with a wavy line on top of electric field to denote that this is the spectral quantity that I am dealing with. Okay. Now, the channel is characterized by having its propagation constant depend on the frequency omega. So, therefore, this is beta of omega. For simplicity, I take the propagation in the z direction with z equal to 0 as the input and z equal to L as the output of the channel. Okay. Now, what is the use of knowing the spectrum? As I have told you, the spectrum, which I am just sketching it, this is not exact spectrum. So, this is in the omega domain, can be thought of as being composed of many different spectral quantities or spectral components. If I consider a particular spectral component, let us say the nth frequency omega n, it will have an amplitude of E of 0 omega n, right. So, what we actually call as the spectrum is essentially the sum of these many different frequency components, each frequency component having a complex amplitude of E of 0 omega n. So, why I say it is complex amplitude, because you know that E of 0 omega is a complex quantity, which means that at every frequency component omega n, you have to give both the magnitude of the complex amplitude as well as the phase angle of that one. So, consequently, you have magnitude spectrum and phase spectrum, which simply tells you that given a frequency omega n, what is the magnitude of the complex amplitude at that frequency and of the phase of that component at the same frequency. So, that is what I mean when I say this is a complex amplitude. So, at every frequency omega n, you have a complex amplitude, but that is not really a problem for us, right. We have seen how, at least in the plane wave case, that if I actually have a certain complex amplitude plane wave or a wave propagating through the distance z, then it would simply acquire a phase shift of e power minus j beta. Of course, since beta is dependent on omega, now we have to explicitly find out which frequency component is propagating, find out the corresponding beta of omega n, which is the value of beta at omega n, and multiply that one by z, z being the distance of propagation. Of course, when you set z equal to L, that will give me the overall phase shift that this particular component has experienced after it has propagated a distance of L units. Okay. So, this nth frequency component actually will become E of 0 comma omega n, which means to say that the amplitude would remain as it is, because we have assumed alpha to be equal to 0, and we simply have a phase shift which is dependent on the propagation constant at the corresponding frequency omega n. If you are not really convinced with this one, think of say the y polarized light propagating through the free space of certain distance z, then the output or after propagation you would have written this as e power minus j beta z, where there you would have assumed beta to be the propagation constant, which is kind of independent of the frequency, but here you really, or beta which would have assumed a certain value. So, in the free space case, beta would be given by omega square root mu 0 epsilon 0 or equally omega by Vph, where Vph is the phase velocity. You would have assumed this one. Now, it is the same thing, except that beta is now explicitly dependent on omega n, and it may not be just the ratio of beta to omega may not be a constant, but it might actually be a function of omega. So, this beta omega and Vph, when Vph is constant, is essentially a linear relationship when you plot beta versus omega, and the ratio of omega to beta would be the phase velocity Vph. But in general, this may not be linear. In fact, we know that it is not linear. For the LP01 mode, what we have shown is that it actually goes something like this, right. This is non-linear function. So, if I hope you understand the idea is still that whatever may be the value of beta at that particular frequency, you take that value of beta multiplied by the length of propagation. So, in general it is a length z, or if you specifically know that the output is at z equal to L, you can put that value of z and then this would be the nth frequency component propagated through the fiber and now arriving at the output. Okay. Of course, my input spectrum is not just limited to one frequency component, it is actually made up of multiple frequency components. No matter what frequency component that I have, all I have to do is to find out the complex amplitude of this particular frequency component omega n and then multiply it by the phase factor e power minus j beta omega n times L. Okay. In continuous domain, what we actually have is the spectrum being multiplied by e power minus j beta of omega times L times E of 0 comma omega, which we will call as E of L comma omega. Okay. So, now one can also define the transfer function of this channel, okay, of length L by looking at the ratio of the frequency transform of the output versus to the frequency transform of the input. So, essentially meaning that I look at the ratio of E L comma omega and E of 0 comma omega, and I will see that this is simply given by this phase term e power minus j beta of omega times L. Sometimes this is also written as e power minus j phi of omega comma L, because you want to also specify the length here, and this phi is essentially the phase spectrum or the phase delay. Okay. Because phase is related to delay, this is sometimes called as simply phase delay, although the terminology is not very nice. It is kind of standard in communication literature. So, we will sometimes refer to this as phase delay, but the transfer function is basically e power minus j beta of omega times L, and this is very important because all you have to do is to take the spectrum at the input, multiply by the transfer function, you will get the output in frequency domain. You then go back to the time domain by taking inverse Fourier transform. Of course, you would have started in time domain E of 0 t, and using Fourier transform you were able to go to E of 0 omega, and once that is there, this is at the input side, you can then multiply by the channel here to actually obtain e to the power minus j beta of omega L times E of 0 omega, which is the Fourier transform at the output. Right now, you apply the inverse Fourier transform to obtain what is E, the electric field at length L or at the output of the fiber, and this is given by your inverse Fourier transform formula. So, if you do not know this, please go back to your signals and systems course, or if you know this and you have forgotten, you will immediately recognize that this is the inverse Fourier transform integral. So, what we have is E of L comma omega e to the power j omega t d omega, there is 1 by 2 pi factor. So, I have just put that 1 by 2 pi factor, and integral of course goes over the range in general from minus infinity to plus infinity, right. Now, I know what is E L omega because that is precisely the output frequency spectrum that I have. So, I will go back and put that spectrum. So, I have E of 0 omega e to the power minus j beta of omega L, right, times e to the power j omega t d omega. Okay. Now, this is the expression that you have. Of course, to properly solve this, you need to know the input spectrum, you also need to know what is the dependence beta of omega, and once you know these two quantities, then you can find out what would be the output. Okay. Let us consider a few special cases. First, consider the simplest case of a free space medium. Okay. I will assume that my light is polarized at say one of the directions, so maybe x polarized light or maybe y polarized light, and then it is not just one component plane wave, but it is actually a pulse. Okay. So, I have E of 0 omega, which is in some sort of a pulse. We do not even need to know what kind of a pulse it is. It could be a square pulse, it could be a triangular pulse, it could be this type of a pulse, it could be any pulse that we consider. Of course, this has to have a certain spectrum that we need to know. So, that spectrum would be E of 0 comma omega, and the output E of L t is given by the same 1 by 2 pi E of 0 omega. Okay. This is E of 0 omega. You have e power minus j beta of omega L e power j omega t d omega, but because this is free space medium, the value of beta as a function of omega will be omega by VPH. Okay. So, this is linear relationship as we have seen, and we will assume VPH to be a constant factor. Okay. So, I mean it is assumed to be a constant. Okay. So, when I substitute for this into this expression, look at what I actually get, right. So, this you can also do in your notebook, take omega as a common factor. So, you have T minus LBH, okay, d omega, right. Of course, there is a 1 by 2 pi here, and what you actually see in this one is that this is the same expression for the inverse Fourier transform of this E of 0 comma omega, except that T is replaced by T minus L by VPH. Okay. And because this L by VPH is a constant, so this T minus L by VPH is just some tau or whatever, that's just a variable of integration is omega, but this frequency or the inverse Fourier transform is now being evaluated at T minus L by VPH instead of T. Okay. So, this is actually E of 0 comma T minus L by VPH. What we mean by this is that if I were to consider the pulse, okay, so I am considering some sort of a pulse like this. Of course, in an actual scenario the pulse will be modulated onto the carrier, and therefore, you would see something like this. So, there is a carrier out there, right, and this pulse, let us say, begins at 0, I mean has some value of minus T naught to plus T naught. I am just taking some arbitrary numbers, because you will soon see that there is no need to even worry what kind of a pulse this is, because this might be the input E of 0 t, that is at the input of the channel Z equal to 0, but at the output of the channel what you have is the same pulse, except now that this will be, this is t, right, t equal to 0, but except now that instead of t equal to 0 you now have the pulse center at L by VPH, because earlier the pulse center was at t equal to 0. Now, to get the same pulse center here, you need to make t equal to L by VPH, and therefore, the pulse center has simply moved to this distance, which is L by VPH, and this delay is what we call as phase delay, and luckily every frequency component that makes up the pulse will experience the same delay, and therefore, arrive at the output at the same time. That is, the pulse, the entire pulse would arrive without any change in the shape. All frequency components arrive at the same time, and when you put the frequency components together and then form the inverse Fourier transform, you would see that the output would remain in the same way as it was at the input. No distortion, although I might not show it correctly, but there is absolutely no distortion, and the pulse would remain without any change in the pulse spectrum. So, no change is an important condition. Okay. So, the phase spectrum for this one phi of omega is given by minus, since I have used e to the power minus j omega. So, I do not have to use a minus here. So, what we have is omega by VPH times L. So, this is the phase spectrum, and we define something called as group delay. Okay. You will soon see why this is called as group delay by d phi by d omega. Okay. In this case, what would be d phi of omega by d omega, that is differentiating phase with respect to omega, you will get L by VPH, and please remember that VPH is constant, L is constant because it is the length of the fiber that you considered, but L by VPH itself is equal to phase delay. So, the group delay for free space is exactly equal to phase delay in this free space conditions. Both group delay as well as phase delay turn out to be equal, and this equality is what causes no distortion in the output pulse. Okay. Now, let us go to, instead of working now with free space, which we used just to understand what was happening, we now want to consider what happens through the fiber. Okay. So, since I am considering the fiber, I know that beta will be some function of omega, correct. So, beta will be some function of omega, but now I am going to assume that my pulse, instead of being just a pulse here, I have actually modulated this pulse onto the carrier, and let me take the carrier frequency as omega 0. Okay. This is how you normally transmit optical pulses. So, we actually go to this kind of a consideration. The procedure remains the same. The transfer function of this one is still given by e power minus j beta of omega times L, and our goal would still be to find out the spectrum here and multiply the spectrum with the transfer function. This is the transfer function, and then once you get the spectrum, you take the inverse Fourier transform and obtain the pulse in the time domain. Okay. So, this is precisely what we want to do, and we will do that. So, first to begin with, and we will, instead of assuming a length L, maybe we will assume a length Z, because we want to just not be considering only at the output. At any distance Z we want to consider. This is also important for our numerical method of understanding pulse propagation, as we will see later. Okay. The idea is still the same, it would propagate it in that way, except now that since I have considered the pulse to be propagating having a carrier frequency omega 0, I need to consider that particular thing. So, I am going to assume that initial pulse that we are going to launch into the optical fiber can be written as some a of 0 t, where a of 0 t corresponds to the amplitude of the pulse or the kind of pulse shape that we are considering, which of course has been modulated by the carrier. So, this is a simple modulation, a double sideband kind of a modulation. So, this carrier is at omega 0, and the spectrum, what would be the spectrum here if I take the Fourier transform? The spectrum would be E of 0 omega, but that would be A, the capital letter A standing for the Fourier transform notation. So, A 0 omega minus omega 0. All that we are saying here is that, look, this A of 0 t was a spectrum or has a spectrum which is centered at omega equal to 0, whereas this transformed one has a spectrum which is sitting or centered at omega 0, and this translation in the frequency is what we have done by multiplying it by e power j omega 0 t, and of course, I am only considering the positive frequency components here, because that is enough for us to understand. Otherwise, I should actually consider both regions, both positive as well as negative frequency regions. Okay. So, this is my Fourier transform. All that we are saying is that whatever may be your pulse shape, that pulse shape is now centered at omega 0. Okay. Now, how do I get the pulse at any distance z, the spectrum of this one at any distance z is to take the initial spectrum and then multiply it by transfer function. Okay. So, that would be A of 0 omega minus omega naught times e power minus j beta of omega z. Okay. Now, it is this one whose inverse Fourier transform I need to take. Now, before doing the inverse Fourier transform, I want to look at this beta of omega. Since my interest frequency range interest is now centered at omega 0, the different frequency components that make up this particular thing can be written in terms of difference with respect to omega 0. What I mean by this is that I can consider any frequency component omega here, and then I can, as long as this pulse spectrum is kind of narrow, small bandwidth kind of a pulse, then this omega minus omega 0 will give me the distance or the difference between the two frequency components, the carrier and the component that I am considering. So, my omega can be either on higher than omega 0 or it can be lower than omega 0, but my reference is now, instead of 0 frequency, it has now become omega 0. Okay. And now you can kind of appreciate what I am doing here. So, I have omega 0, okay, which is my carrier, which is what I can actually, I mean, I know beforehand, right. I can express this beta of omega for any frequency omega that is slightly away from omega naught, that is slight deviation from omega naught. I can write this beta of omega as Taylor series as beta of omega 0 plus what is the difference between these two, omega minus omega 0 times del beta by del omega evaluated at omega 0. What is del beta by del omega or d beta by d omega? This is the differential of beta with respect to omega, okay, but evaluated at omega 0. In literature, this term is called as beta 1. Okay. So, then the next term would be omega minus omega 0 square by 2 del square beta by del omega square, again evaluated at omega 0. It turns out that this del square beta by del omega square is actually written as beta 2. Okay. Of course, this beta 1 is a function of the frequency omega 0, beta 2 is also a function of frequency omega 0. So, this is the Taylor series expansion as long as the pulse spectrum is kind of narrow. It is narrow because this omega 0 is usually in terahertz or teraradians per second, whereas the spread or the frequency spectrum will be in a few tens of gigahertz. So, it is actually kind of factor of 100 smaller. So, you do not really need to worry about this particular approximation being invalid. Okay. Any case, so I have beta of omega and I have written terms only up to second order. Okay. So, now since this is how beta would actually vary, I have just made a small Taylor series expansion of beta around omega 0, I can go back and put that into this transfer function. Okay. So, when I put that one, the electric field at the distance z after propagating through the fiber would be A 0 omega minus omega 0. This is the original pulse spectrum that is centered now at omega 0, and then you have e power minus j beta 0 z. By now you know that you would have guessed that beta 0 is essentially beta at omega 0. Then you have the next term which is e power minus j omega minus omega 0 beta 1. Please remember, beta 1 means the first derivative of beta with respect to omega times z. The next term will be e power minus j omega minus omega 0 square, correct. This would be omega minus omega 0 square by 2, right, and then you have beta 2 times z. Okay. So, this is the transfer function. Now, what I need to do is to actually go to this spectrum and then write down what is E of z t, which would be inverse Fourier transform of. So, we have the electric field at the output given by this expression. I hope you can see all the expressions that is here. So, you have the initial power spectrum or the initial pulse spectrum, and then this e power, there are 3 terms to e power minus j beta of omega z, right. So, these are the 3 terms: carrier, the first term beta 1, then beta 2, and then you have e power j omega t d omega. So, now look at this, this entire thing is actually a function of omega minus omega 0 rather than omega. So, what I can do is I can multiply inside the integral this quantity e power j omega 0 t and minus j omega 0 t. So, that the product is actually equal to 1 and I have not changed anything here. And once I do that, I actually have a term that would be a function entirely of omega minus omega 0, which I will call this as capital omega, where capital omega is by definition equal to the deviation from omega 0, which is omega minus omega naught. Okay. So, I have a of 0 omega, I have e power j omega 0 t minus beta 0 z. This I obtained by combining this term with this term. Okay. Then I have a term which is e to the power j. By combining this one with this one, I have e power j omega minus omega 0 is what we have called as capital omega. So, I have capital omega t minus beta 1 z. Okay. That as I told you, can be obtained by combining this one with this term e power minus j omega 0 t and combining it with the term which has beta 1 at the top. Okay. Then you have e to the power minus j beta 2 omega square by 2 d omega. Okay. The integral limits of course would still go technically from minus infinity to plus infinity, but this is the expression that you were looking for. Now, we can actually go back and combine this term slightly better. We know that since the integration is with respect to capital omega, this term in the curly braces is actually of no use for us because it is independent of that omega. So, I can actually pull that outside of the integrand. So, when I pull that outside and further take omega 0 as a common factor, I get t minus, so I get beta 0 by omega 0 times z. Okay. That would be the factor that is independent of whatever is the integration, and then the integral can be written by writing this a of 0 omega, which is the spectrum, with e power minus j beta 2 omega square by 2 times z. Sorry, I forgot the z here. This term I will combine it into a 1. Of course, if someone gives me the pulse spectrum, then I will know what to do with this expression, but until that I do not know what this expression is. but I have e power j omega t minus beta 1 z integration with respect to omega. Now, since the term that is written in this square bracket is the term on which we are operating the inverse Fourier transform, except that we are now evaluating this inverse Fourier transform not at this one not at t equal to 0, but or rather at t variable, but at t minus beta 1 z. Okay. This entire term on the right hand side can be written as inverse Fourier transform of a of 0 omega e power minus j beta 2 omega square z by 2, okay, evaluated at t minus beta 1 z, okay, multiplied of course by the carrier term e power j omega 0 t minus z by omega 0 by beta 0. Okay. This small simplification, I mean this change actually gives me a small simplification, because omega 0 to beta 0 is actually equal to the phase velocity Vph of the carrier. So, this is actually the phase velocity of the carrier, and z by velocity is the delay of propagation of the carrier over a distance z. Okay. So, this term can be even written as e power j omega 0 t minus z by Vph. This is how the carrier would have changed, or this is how the carrier is propagating. The carrier experiences a delay of z by Vph. Okay. Normally we talk about delay per unit length. So, that means that your actually normalized delay or delay per unit length is given by 1 by Vph, okay, and Vph itself is inversely proportional to beta 0. Okay. The term on the right hand side is essentially how the fiber has modified the spectrum. We started off with a spectrum of the amplitude or the pulse shape a of 0 omega, that needs to be multiplied with the second order beta 2 value, which is called as the second order dispersion term e power minus j beta 2 omega square z by 2, and whatever that you get, that would be the spectrum of the pulse, okay, which would be in general distorted, and this spectrum is now propagating at a velocity called as group velocity, and group velocity is inversely proportional to, or I think directly proportional to, group velocity is inversely proportional to beta 1. Okay. We are going to say more about this. We are going to discuss how to understand dispersion effect numerically and study pulse propagation through the fiber with different dispersion regimes in the next module. Thank you very much.